Now that we know how to work out limits by looking at the graph, let's see how to do it using algebra. When we say we're finding a limit algebraically, it basically means we don't have the graph. We're just working with the function in its algebra form. To figure out the limit algebraically, we just need a solid game plan. Don't stress. It's way easier than it looks, and we're going to tackle it step by step together. Our game plan starts by substituting the limit approach into the limit itself. Remember, the limit approach is that little value written underneath the limit sign. So all we're doing is taking that value and plugging it straight into the expression. Once you've done that, you'll see we can get one of three possible outcomes. And this is super important because we deal with each of those outcomes in a different way. The first outcome you can get when you substitute the limit approach is that the example works out with no issues, like the one we did together. You plug in the limit approach, and you get something you can literally throw straight into a calculator with no drama at all. Whatever answer you get, that's the answer for your limit. Easy as that. The second outcome we can get is when you substitute the limit approach and try to punch it into a calculator, and boom, you get a math error. Let's check out the next example. When we substitute the limit approach and punch it into the calculator, we get a math error. That means algebraically, something's not adding up. If we look closer at the example, we'll see the reason we got a math error is because we ended up with 0 over 0. And we all know in maths, you can't divide by 0. This situation where you get 0 over 0 is called an indeterminate form. We'll dive deeper into that in later videos, but for now, we just need a plan to get rid of that math error so we can actually find the answer to the limit. In a limit, when we get 0 over 0, the way we fix the problem is by factorizing and canceling out terms. That's how we get rid of the issue and actually work the limit out. Let's try that example again, where we got 0 over 0. If we factorize the expression, you'll see we get a bracket that's the same on top and bottom, which means we can cancel it out. Once we've factorized and canceled, we try plugging in the limit approach again, and boom, no more math error. We get a proper answer for the limit. Easy as that. The third outcome we can get is when we plug in the limit approach and still get a math error. But this time, what's causing the math error is different from the one we just did together with the 0 over 0 situation. Let's check out an example to see what's going on here. In this example, you'll see when we plug in the limit approach, we still get a math error, but this time, the cause isn't 0 over 0. What's causing the math error now is that we've got a normal number divided by 0. And we all know in maths, you can't divide by 0, no matter what. When we get a math error because a number is divided by 0, factorizing won't help. You can usually see in the example that there's nothing to factor out. So, how do we fix the math error and still get an answer for the limit? We use something called a sign analysis test. The sign analysis works like this. We know when we plugged in the limit approach of 4, it gave us a math error. What we want to test now is what happens just before 4 and what happens just after 4. Because remember, when we started with limits, we said a limit cares about what the function is doing as it gets closer to a certain x value. The limit doesn't actually care what's happening exactly at that x value. So what we're going to do now is plug in values just before 4 and just after 4 to see what answer we get. When we plug in the value just before 4, this is the answer we get. And when we plug in the value just after 4, this is the answer we get. In sign analysis, we only care about the signs of the answers, not the actual numbers themselves. That's why it's called sign analysis. So if we focus just on the signs, you'll see our first answer is negative and our second answer is positive. Now, for the limit to exist, these signs have to match. Both need to be positive or both need to be negative. If the signs are different, it means the limit doesn't exist at that point. So in our example, since the signs don't match, the answer is that the limit does not exist. If both signs were positive, the limit would have existed, and the answer for that limit would have been positive infinity. If both signs were negative, the limit also would have existed, but then the answer for that limit would have been negative infinity. This is all going to make way more sense when we break down why we get these answers for each of the three options by actually looking at what it would mean if we had drawn the graphs for these limits. We'll dive way deeper into this in future videos, where we'll break it down step by step and actually sketch the functions. You're now able to work out limits without even having the graph, just by following a simple game plan. Winging calculus is like winging a parachute jump, fun until the ground shows up. Ditch the 30 open YouTube tabs at 2 a.m. trying to integrate and grab my ebook course, step-by-step fixes and shortcuts. Cheaper than your monthly coffee bill and way easier than explaining a flatlining GPA. Course link in the description. If this helped, smash like and subscribe. See you next time. Cheers!